Okay, good morning. Today we'll continue with chapter 6, and we'll look at the filters. But before I do that, I just wanted to point out the final exam page. It's been there since the beginning of the quarter. And so let's see. Should be this one. So if you click on the final exam link from the front page, it will take you to everything you need to know about the final exam. As I state up front, please read everything on this page. There are several students who have already done this and actually filled it out, submitted the form in the first week of class itself. Final exam is not, I won't go over everything right now because it's there, just read it. If you have any questions, reach out to me. The first thing I'd like to point out is that it's worth 20% of your grade. This is something I also mentioned and went over on the first day of class and from the syllabus itself. It's mandatory, it's not optional, meaning I do not drop the final exam. There are a lot of extra credit points built into my course, and so there will not be any other curves because of all of those extra credit points. You can choose not to take the final. That's up to you as an individual person. It's worth 20% of the grade, but if you're happy with your grade as it is, you can just not take the final. That's up to you. There are 4 options for section 3. This is what I'll point out. Section 3 is this class at 10 a.m. The exam is in this room on a Wednesday at 10 o'clock in the morning. Okay, that's the university scheduled date and time. You can find links to the university schedule right here in these 2 points right there in these 2 links. And you can use these, of course, to figure out when your other finals are. Okay, so if your other instructors have not posted it yet, you can use these links. Again, these are determined by the university. This is not up to faculty, right? It's determined by the university. So your university scheduled day and time is Wednesday at 10 o'clock in this classroom. There are other options. If you wish to take it at 7 a.m. on the same day, that's section 02 on a Wednesday. You can also choose to take it on a Friday with the other section. And then finally, there is a Saturday option, which is the Saturday before finals week. It's the Saturday after the last day of class. Last day of class is on a Friday. The next Saturday, I have scheduled the final at 1 o'clock in the afternoon. That will not be in this room. That will be in the EE building. It'll be a different room. And what I will ask students to do is you submit. So there's topics, equation sheet. All of the information is in there. There's a survey at the bottom of this page. As I mentioned, several students filled it out in the first week of class itself. If you plan to take it on any other alternative time, you need to fill out this form. Okay, especially if you wish to take it on a Saturday. Because it's not in this room, I need to know how many students will appear on Saturday so that I know which room I need to reserve and how many exams I need to print. If you plan to take it in this room, either on Wednesday or on that Friday of finals week, I'll have plenty of spaces. There are physical seats that are available. So I do not foresee a problem for those alternative times. But fill out and submit this form if you wish to take it at any alternate time. You do not need to fill it out. You do not need to submit this form if you're taking it at its regular time, which is 10 o'clock in the morning on that Wednesday. Okay. All right, read through this entire page. As I stated up front, please read everything on this page and then reach out to me if you have any questions. Okay. All right, let's get to our topic, which is filters. We stop right here, which is the frequency response of a network solely from the transfer function, right? Which is similar problem on the homework itself. So now we look at 4 different filters today. We will use the component behavior at either low frequencies or high frequencies to describe each filter circuit. Okay, I call this my handy dandy table, and using this handy dandy table, we can perform a very quick analysis of any circuit that contains a inductor or a capacitor. All right. So we'll model the behavior of an inductor or capacitor at both low frequencies as well as high frequencies. For a capacitor, the impedance is 1 over J 2 pi Fc, F times C. The impedance is inversely proportional to the frequency value. For an inductor, it's the exact opposite. ZL is 1 over J 2 pi FL. So ZL is directly proportional to the frequency. And I'll again remind you that frequency in hertz is related to the angular frequency omega by 2 pi f. So ZC and ZL, sometimes you would hear J omega L and 1 over J omega C. Again, it's the exact same thing. You have a time domain expression, right? Frequency F in hertz, and you translate that as a vector. It's angular frequency in the frequency domain. So omega is omega is 2 pi F. One full circle, 360 degrees, 2 pi. Hence, omega is equal to 2 pi F. So it's the same exact equation. Anyway, so at extremely low frequencies, when F or omega tends towards 0, capacitor behaves like an open circuit. And I like to call that as OC. Right? Short for open circuit, OC. So as frequency F tends towards 0, capacitor behaves like an open circuit. Think back to chapter 3. You apply a constant DC voltage to a capacitor, it reaches full charge. There is no more charge in balance, and hence capacitor behaves like a short circuit. Current stops flowing in the circuit, right? At the same time, if you apply extremely low frequencies to an inductor, it behaves like a short circuit. Reaches full charge, voltage across the inductor drops to 0. This is basically DC behavior. 0 hertz, meaning the value of that signal is not varying with respect to time. It is a constant value. 0 hertz means it's DC, it's a constant value. Inductor behaves like a short circuit, or SC for short. And at extremely high frequencies, when F tends towards infinity, extremely high frequencies, capacitor behaves like a short circuit because it's constantly charging, discharging, charging, discharging, charging, discharging. So current is constantly moving in that circuit through that capacitor, right? Constantly reversing. And inductor is the exact opposite. Inductor behaves like an open circuit, or OC. Again, capacitor and inductors, the mathematics is beautiful. The natural physics is also beautiful about it. They are very similar in many ways, but they're also exactly the opposite in many ways. And that allows us to build modern electronics that we use in everyday life. Okay. So again, I call this the handy dandy table, and you can use this table to describe or to analyze the behavior of any circuit containing inductors and capacitors very quickly and very efficiently. And we will use this today. Okay, we'll use this today. So if you think back to chapter 4, I mentioned if you use a capacitor in a circuit, we have a RC circuit. If you use an inductor in a circuit, you have a RL circuit. It's the same thing with these filter circuits. If you use a capacitor to build a filter, it is a RC filter. If you use an inductor, it is a RL filter. And you can use both inductors and capacitors to create low pass as well as high pass filters. Low pass meaning it allows low frequencies to pass through. High pass meaning it allows high frequencies to pass through. Okay, so the filters we study here are low pass and high pass filters constructed out of both inductors and capacitors. So you have RC low pass, RC high pass, you have RL low pass and RL high pass filters. They are very similar. In fact, if you take a look at the low pass and high pass, which we'll just do in just a few minutes, it's exactly the same circuit. Okay, it's exactly the same circuit. If you combine both if you combine a low pass and a high pass circuit together, you get what is known as a band pass filter, BPF, band pass filter. Okay, and most filters that we use in everyday life are band pass filters. It will only allow a certain band of frequencies to pass through. Everything else is blocked. Remember the examples I used on Monday, where every wireless network provider has their own band of frequencies that it allows on their network. And so everything else is blocked. Only those certain band of frequencies are allowed to pass through. So most filters we use in everyday life are band pass filters. And depending on the band that is allowed to pass or be rejected, we get a band stop or band reject filter. Okay, band reject filter. So this is a cross matrix. Cross matrix. Okay, you can have RC low pass and RC high pass, and you can also have RL low pass and all RL high pass filter. 2 by 2. Thinking back to chapter 4, I also mentioned, or if you recall, a one energy component device circuit requires a first order differential equation. It is known as a first order circuit, and hence a filter circuit built out of RC or RL, meaning only one energy storage component, is a first order filter. Okay, so if you build your filter circuit out of only one energy storage component, either a capacitor or an inductor, it is a first order filter. If it's two components, it's second order. If it's three, it's third order, and so on and so forth. Okay, the only second order filter we look at here is the RLC filter. It contains both inductor and a capacitor. We do not look at any higher order filters in this class. In fact, even in an E major class, when we introduce the topic of filters, we only look at first and second order filters. Filters by itself is a highly complex subject, a highly complex topic, and there's an entire course devoted. Actually, there are multiple courses devoted to filters and filter design. Okay, so those are just higher level classes, or even for EE majors. All right, let's look at the first one, which is a RC low pass filter. Okay, RC low pass filter. What is the first thing we notice? We notice that there is a voltage source on the left, and we are taking the output across the capacitor. And we are taking the output across the capacitor. But think back to chapter 1, series and parallel connections. Okay, series and parallel connections. We have the resistor and capacitor connected at one single node, which is right here. Right? It's connected at the top node. It seems as if there is a third connection to that node. But is it really? No, you're simply measuring or taking the output at that point. Okay, you're simply taking the output across the capacitor. There is no other component connected at that node. So if there's no other component connected at that node, what does it mean for the resistor and capacitor? They are in series, absolutely. They are in series. And there's a point I'm trying to make with this. the circuit is actually like this. Okay, the circuit actually looks like that. You're applying a voltage V in, and you take the output across the resistor. Across the capacitor. Passive reference configuration applies. Everything still applies exactly the same. When current passes through, the point of entry is plus, point of exit is minus. If you take the output across the capacitor, the positive notation will be at the point of entry, which is at the junction point of the resistor and the capacitor. Okay. Now, obviously, I have it in the title that this is a low pass filter. So if I take the output across the capacitor, it is the low pass filter. What I will tell you is that this is a series connection. And if you take the output across the resistor, it is a high pass filter. That's it. There is actually no difference in the circuit configuration of a low pass and a high pass filter. You take the same series circuit of a resistor and a capacitor. If you take the output across a capacitor, it is low pass filter. If you take the output across the resistor, it is a high pass filter. And I will explain how and why that is. We'll first do a quick and easy analysis using the handy dandy table. And then we'll also look at the transfer functions, the mathematical ones. Yes. Voltage. VR. Yes. V out. Would be the high pass. It will function as a high pass filter, meaning it'll only allow high frequencies to pass through. The lower ones will be blocked. So V out, if you take across that resistor, will have a lower voltage at low frequencies. And at higher frequencies, the V out would be very equal to V in. And we will see that in the graphs and the charts. Yes. Yeah. Yes. So high pass HPF, if you take the output across the resistor, so it's plus minus here. And if you take the output across the capacitor, it's low pass, meaning only low frequencies are allowed to pass through. Yeah. Again, this is just an initial point that I'm making, but we'll look at the explanation in just a few seconds. In real life, this is also the reason why you have cheap speakers or inexpensive ones versus a more expensive system. So if you use the example of a speaker, an audio system, you have the small speakers, the cube types. They look very cute and they don't take up much space. Sometimes you have two-way speakers, right? So there's a small woofer in there and there's a small tweeter mounted right on top. Really cheap or inexpensive speakers. And I kid you not, I've seen speakers which will simply have a resistor and a capacitor with two of their leads just twisted together. That's it. And they will be soldered or mounted directly on top of those two speakers. No circuit board, nothing. It'll just be like a resistor and a capacitor. And both the outputs, obviously, this would go into one speaker, the small woofer or the tweeter, and this output would go on to the second speaker, which would be like right on top of each other. Something like this right here, this is a two-way speaker, but it's a big box. So I would assume that it has a more expensive circuit inside it. Like the big professional speakers that we use for like DJ audio systems, they have like big crossover networks like inductors and resistors and capacitors. Much better filtering behavior. The cheap ones, if you have like something lying around, you can just open it up and take a look at the back. And you will see that it will have just a resistor and a capacitor mounted on top. Okay. Anyway, so let's look at how and why this would work as a low pass filter, right? The quick and easy analysis from our handy dandy table. A capacitor at low frequencies, when F tends towards 0, behaves like a open circuit, right? You can reference the table, you can have it in your equation sheet, that is absolutely fine, right? But as F tends towards 0, capacitor behaves like an open circuit. If you need help in remembering this, 0 and O for a capacitor, right? 0 and O for a capacitor, C. So capacitor behaves like an open circuit as F tends towards 0. So if you replace the capacitor with an open circuit right there, what do we see at the output? V out would be equal to V in, right? You're trying to measure the voltage across the capacitor. That would simply be equal to V in. So at high frequencies, the V out level is exactly equal to the input voltage. Okay. That makes sense? Yes. I mean, we would, but this is just a quick analysis. But if it behaves like an open circuit, no current is flowing. If no current flows through it, then the voltage across that resistor is equal to 0. Again, this is just an ideal theoretical analysis. Yes. The input signals that we are applying to the circuit has a frequency that is equal to 0. So if you apply, let's say, hundreds or thousands of different signals here, V in, the frequency varies. And if the value of the frequency signal is equal to 0, if V in has a frequency that is equal to 0 or is very, very low, then the capacitor will have very high impedance. Approaching 0 or low frequencies or has a value of 0. In this case, they all mean the exact same thing. And then as it tends towards infinity or very, very high frequencies, capacitor behaves like a short circuit, exactly opposite. If it's a short circuit, what do I expect my output to be? If it's a short circuit, both points are joined or connected together, meaning the potential at both ends of those terminals is exactly the same. So what is my V out? 0. So V out is reduced to 0. Any current that's coming through the circuit is just passing through. Okay. So at low frequencies, V out is equal to V in. Right? Low frequencies, V out is equal to V in, meaning low frequency signals are allowed to pass through to the output. But at high frequencies, when F tends towards infinity, V out drops all the way to 0. That means low frequency signals are allowed to pass through to the output. High frequency signals are blocked, and hence it works or it functions as a low pass filter. Low frequency signals are allowed to pass through to the output. That is the effect of the capacitor working at low and high frequencies. An ideal filter, if you plot the output characteristic as a function of frequency, and this is V out. So V out as a function of the input frequency. Let's say V in had a frequency of 0, right? Output V out would have a value equal to V in. If you increase the frequency to 1 hertz, 2 hertz, 3 hertz, and so on and so forth, it would still be equal to V in. Until it reaches a point, and that point, again, I'll explain in just a little bit, until it reaches a certain point where the output drops all the way to 0. And all frequencies after that would have a value of 0 volts because the output is being blocked. This is, of course, the characteristic of an ideal filter, not real. So this is known as the pass band. This is blocked. Okay. all frequencies lower than a certain frequency point are allowed to pass through to the output, meaning the voltage for those frequencies would be equal to the input voltage, and all frequencies higher would be blocked. So low frequencies are being passed, higher ones are blocked. And low and high is relative. Okay, I was just having this discussion with a student in the previous section, meaning what qualifies as low and what qualifies as high. If we use the example of human hearing is within the range of 20 hertz to 20 kilohertz, right? So it's less than, it's barely into the kilohertz range, considering the wireless spectrum that we use today, right? People like me probably can't even hear higher than 15 or 16 kilohertz. So you wouldn't even make it to 20, right? And so low or high frequencies is basically relative. 16 kilohertz or 20 kilohertz for humans would be considered, for human hearing, would be considered as very high frequencies. But if you think about your wireless routers or satellite signals, mobile communications, they are in the megahertz and the gigahertz range. A wireless router works in the 2.4 and the 5 gigahertz band. So for a 5 gigahertz band, kilohertz is nothing. Kilohertz is a low frequency. Whereas for human hearing, it is considered to be high frequency. So low and high is relative. It depends on the application. Does that make sense? Right? So, just as a separate point, humans, of course, as we age, our body starts creaking, which I realized a few years ago. And then, of course, consequences of, loud music during my younger days, during my youth, of course, now you pay the price. Anyway, coming back to the quantitative analysis. We can analyze this circuit in the exact same manner that we did for resistors in chapters 1 and 2. It's a series connection, right? And so series connection will have the same current I flowing through each component. And these are all phasors, right? Complex quantity. So these are all phasors. So the same current I flows through the entire circuit because it's a series connection. I can be determined as voltage V in divided by the total equivalent impedance in the circuit, which would simply be R plus ZC. Again, this derivation is not important, especially we don't do this for the non-EE major classes. V in over ZEQ. ZEQ in this case comprises just of the resistor and the capacitor impedance. That's it, right? R plus ZC. So this gives you V in over R plus 1 over J 2 pi FC. V out, the voltage for V out would simply be I times ZC. We're taking the output. So we're just two applications of Ohm's law. We're taking the output across the capacitor. So we want the capacitor voltage, VC, because V out is equal to VC. And VC in this case, simply apply Ohm's law, I times ZC. And you plug in I from here, and ZC is still 1 over J 2 pi FC. You have V in, V out on the left, you have V in on the right. You take everything else except V in, and V in translate onto the other side of the equation. You get V out over V in, which of course describes H of F, or the transfer function. There is a derivation. Again, it's simple. You simply insert ZC here and I from this equation, and you solve it. You rearrange the terms to get V out over V in, and you obtain an expression or the transfer function H of F that looks like this. One over 1 plus J F over FB, where F is the variable, right? The transfer function is a function of the frequency. So f is a variable that can take on multiple values, and fb is a constant that is described by this equation right here. For a RC filter, RC first order filter, this is given as 1 over 2 pi RC, R times C. Okay, that's a constant, and it depends on the values of the components. So design engineers would use this equation to describe or to design their filters. FB is known as the cutoff frequency or the break frequency. So the B comes from break frequency. It is also known as the cutoff frequency. Cutoff frequency FC, subscript C. So if you take a different class with a different professor, uses a different book, you might come across FC. Yes. Yes. Yeah. Good. Okay. So it's break frequency or cutoff frequency. And one other point I'd like to make is that this is frequency in hertz. But many books would use omega. Omega, of course, is 2 pi f. Again, remember from chapter 5, frequency in hertz is basically in the time domain. You have time on the x-axis. You translate that into the complex plane in the frequency domain. It's a vector that is rotating inside the complex plane, right? So omega is 2 pi f. One full circle is 360 degrees, 2 pi radians, hence 2 pi f. So this fc could also be described as omega c, which would simply be rc. This also means f is omega divided by 2 pi. Okay, but we'll work with frequency f in this class. Everybody clear on that? Okay, so what is the significance of FB, the break frequency or the cutoff frequency? Right, that's the point where the filter is cutting off and dividing the pass band and the block bands. It doesn't matter what kind of filter it is, whether it's low pass or high pass or band pass. It is the line, it's the border between the pass and the block bands. Okay, so for a low pass filter, passing the low frequencies, the break frequency is describing that all frequencies that have a value lower than FB will be allowed to pass through. All frequency signals higher than FB will be blocked. Okay, FB is the dividing line between the pass and the block bands. So for a low pass filter, the FB describes all frequencies lower than FB that will be allowed to pass. All frequencies higher than FB will be blocked. Make sense? Right? For a high pass, it's the exact opposite. For a high pass filter, the FB denotes the line where the lower frequencies are blocked and the higher frequencies are allowed to pass through. Hence, high pass filter, HPF. Make sense? Right? For a high pass filter, the transfer function is different. Let's take a 10-second pause. Think over this and let me know if you have any questions. Okay. You won't do any circuit analysis beyond this point, right? The important point is we need to obtain the transfer function. Okay, transfer function. The transfer function, again, is a ratio of the voltages, the phasor voltages. So it has magnitude and phase. All right, any questions? All right. So then if I go to RC high pass, meaning if I take the output across the resistor instead of the capacitor. Yeah, and remember, this is the exact same circuit. It's simply the connection that makes it look different, but it's not different. It's the exact same circuit. Instead of taking the output across the capacitor, you are now taking the output across the resistor. The derivation for the equation remains the same. You apply Ohm's law to find the total current flowing through the circuit. And you apply Ohm's law again to find the voltage across that resistor. You'd simply apply Ohm's law, V equals IZ, to find I. It'd be V in over ZEQ. And then, of course, VR would be equal to I times R. And you solve that transfer function. Sorry, you'd solve that equation and obtain the transfer function that looks like this. The denominator is exactly the same. The numerator changes. Numerator is not 1 anymore. You get JF over FB divided by 1 plus JF over FB. The term remains the same. You have an extra quantity in the numerator. F is still the variable. The transfer function is a function of that variable F, which is the input frequencies. FB is still the break frequency, the cutoff frequency. And for a RC filter, it still remains the same, 1 over 2 pi RC. Okay. So if you have a filter made out of or built out of a capacitor, the break frequency remains the same. Doesn't matter whether it's low pass or high pass. Again, we've seen it doesn't matter why, because it's the exact same circuit. If you take the output across the capacitor, it is low pass. If you take the output across the resistor, it is a high pass circuit. Sorry, high pass filter, not circuit, high pass filter. All right, questions? Yes. Well, FB is a constant. So if the component values are given, we can determine FB from the component values. Oh, will F be given in the problem? Got it now. Yes. So it depends on the input V in. Yes. So we'd extract the information from the given problem statement. Yes. Okay. Any other questions? Yes. Yes, I was going to show there was a V in here which had multiple components, but I don't have it written. I don't have it as part of the problem statement. That's what I was trying to show. So this is an example problem where we are supposed to determine what the output is. And the V in has 3 components. So similar to the example problem that we did on Monday and the problem in the homework, it has 3 components, and each one of those will have different frequency values, and we'd equate it with the standard form and extract omega information from there and the frequency information F from there. And then for every component, we will see how the filter will affect each of those components. So in example 1 that we did on Monday, we had a transfer function that was described to us graphically, right? Here, we just do a mathematical calculation and apply the equation from the transfer function that is given to us. So we'd first determine what kind of filter this is, then we'd know which transfer function to use, and then we'll take it from there. But we don't have enough time to get to that problem today. All right, any other questions for the low pass filter? Okay, so the behavior of a low pass filter when plotted as a function of frequency would look like this. All right, it has a gentle slope, Ideal filters, of course, we would want something like this, where on the left is pass, and the right is blocked. That is the magnitude of the transfer function h of f plotted as a function of frequency f. Okay, it's the magnitude of the transfer function, and it's a normalized function. Hence, the maximum value is 1. Okay. Again, transfer function is the ratio of the output voltage to the input voltage, right? So when the output voltage is exactly equal to the input voltage, you have 100% of the output, which is 1. And then as you go along, at some point, it starts dropping off. Which point do we take? Right? What point do we take as the demarcation line between pass and block? That would be FB, of course. But in real life, it would never be a sharp cutoff. It'd always be a gentle slope. So the point, the demarcation line, is taken where the power, the input power drops, sorry, the output power drops to 50% of the input power. Okay. We are monitoring the output. After cutoff frequency, the output voltage and the output power should drop to 0. But in real life, you would never get 100% 0. Right? It's just not possible. So the point at which we take or we consider the pass and the block band is the point where the output power drops to 50% of the input power. And we consider that as the cutoff frequency or the break frequency. The value of the output power drops to 50% or less beyond the cutoff frequencies. In terms of voltage and in terms of the magnitude of the transfer function, it turns out to be 0.707. So 70.71% of V in. And you can quantitatively or mathematically find that value when you plug in F equals FB in this equation. Remember, F is the variable, is the input variable. It takes on multiple values, right? So when F is less than FB, you have a value that is higher than 70%. When F equals FB, you get 1 over 1 plus J. 1 over 1 plus J, right? When you solve that, when you find the magnitude of that function, it comes out to be 70.707, 70% of the input voltage. Okay, so for a low pass or a high pass filter, the cutoff frequency is the point where the output drops to 70%, okay, or 70% or less. The phase angle is also affected. The phase of the transfer function goes from 0 to minus 90. 0 to minus 90. Okay, 0 to minus 90. At the cutoff frequency, it is minus 45. And this will be true for all filters, all low-pass filters, whether made out of capacitors or inductors. Okay, capacitors or inductors. So if you look at a RL filter, it's exactly the same as a RC filter. It's a series connection of the inductor and a resistor. And depending on where you take the output, you obtain a low pass or a high pass. Okay. If you take the output across the inductor, you get a high pass filter. If you take the output across the resistor, you get a low pass filter. This is L and this is R. Circuit analysis remains the same. It's a series circuit. So you have total current I. The total impedance is R plus ZL or J omega L, J 2 pi FL. Output across the inductor is I times ZL. Output across the resistor is I times R. When you derive the transfer function, actually, this is I is V in over ZEQ. And then VR is simply I times R. And VL is simply I times ZL. Okay. When you perform that derivation and you rearrange the terms to obtain the transfer function, you get the exact same equation as we did for the RC low pass filter. 1 over 1 plus JF over FB. No difference. Because that transfer function describes a first order low pass filter. Component value does not, the component does not matter. It does not matter whether it is made out of a capacitor or an inductor. The break frequency, however, depends on the components, and so that is different. It is FB is equal to R over 2 pi L. Omega or omega C cutoff frequency would simply be R over L. If we look at the output across the inductor, we get a high pass filter. Transfer function is exactly the same as a RC high pass filter. JF over FB. And then FB remains the same as for a RL filter. FB is equal to R over 2 pi L. So again, cross matrix of 4 filters, low pass and high pass filters built out of RC and RL, but it's actually just 2 circuits. It's exactly the same circuit for a low pass as well as high pass. Doesn't matter whether you make it out of a resistor, whether you make it out of a capacitor or an inductor. The only difference is where you take the output. Okay, if you take the output across a capacitor, it's a low pass filter. If you take the output across a resistor, it is a high pass filter. No difference whatsoever. The transfer functions, the equations remain the same. The break frequencies for the components remain the same. All right, questions. We still have a couple of minutes, so we'll devote that time to any questions that you may have. Again, as I said, there is an example problem, but we won't have time to get into it right now. So I will post a video right after class, probably about 30 to 40 minutes after class, based on that example problem. All right, I'll end class here today. We'll pick up here again on Friday, and we'll finish up chapter 6. Quiz will be based on chapter 6 next Monday, depending on how much material we cover. Please take a look at the next homework in line. It already has a due date. I think I set it to Friday, I believe. I'm not certain right now. So please open up the next homework, okay? All right, if you have questions, I have 10 minutes before my next section begins.